Okay, we're gonna look at setting up and looking at how to approach problem 13.9. In this case, problem 13.9, an athlete is holding 30-pound weights at a height of 6 inches above the stack as shown. Okay, so this is the illustration here. To lower the weight, she applies a constant force of 5 pounds to the handle. Okay, that's right here. Determine the velocity of the weights immediately before they hit the stack. Okay. So she's going to be kind of pushing these back in, but she's got 5 pounds on each one of these. Now, as we look, the way that this is here, here's our stack. Notice that it has 1, 2, 3, I call them supports. And if you follow the tension in that cable, it would be 5, 5, and 5 pounds that's actually supporting this stack right here. Okay, so I'm going to draw the illustration, and then we'll kind of, get the information. So, and then, add in the stuff that they have there. So this is problem 13.9. Okay. The tension in that cable is 5 pounds per the statement. So this is 5 pounds, 5 pounds, 5 pounds. The stack itself is 30 pounds, right? Of that chunk that she's lifting. And then down here, this is the rest of the stack. This distance is, it says 6 inches, but I'm going to put 0.5 feet just because we know that our distances that we're using is going to be in feet. We want to find V2, okay? And that's going to be the velocity when this hits down here, okay? So we're going to use that work energy theorem, okay? Because we have a distance here and we're trying to find a velocity, so it kind of makes sense to do that. So we know that the work energy theorem is going to be T1 plus U1 to 2 is equal to T2. Now, they're only talking about her having the 5 pounds as it goes, from this 5 or this 0.5 foot or 6-inch distance down. So our assumption is we're analyzing this starting, if you would, at 0 before she starts lowering it. So T1 is going to be 0. So then we have the work and we have the kinetic energy. Okay. So our work, okay, work 1 to 2 is going to be force times distance, right? So force times distance, as we look here, our distance is vertical and we have our force here, right, pulling down, but we also have the support forces going up, okay? So if we look at the, if you would, resultant force that's occurring here, we would say that we would sum our forces in the y, and this is just equal to 0, so we can solve for what is the resultant force here. And we would say that we would have a positive 15 pounds minus 30 pounds, right? And then that's going to be equal to our force. So if we subtract these two on this side, we're going to get, what are we going to get? 15. So this would be a negative 15, right? Negative 15. Why am I at a loss for this? Yeah, negative 15, right? Now we're going to use that up here in our force. So this is going to be a negative 15 pounds times a distance of 0.5 feet. Okay. So if we multiply those out, our work is going to be a negative 7.5 pound feet. Okay. Now the T2. T2 is going to be equal to 1/2 mv squared. Okay. So this is going to be our V2 squared. And this is going to be equal to 1/2 times, this is going to be 30 pounds divided by 32.2 times the velocity 2 squared. Now we don't know what that velocity 2 squared is, so our T2 is going to be multiplying this out. So it's going to be 0.4658 times V2 squared. And that's the form that we have to leave it in. Okay. And then now what you're going to do, and I'll let you finish that problem, you're going to plug those back into here and solve for the V2. Was that far enough for you, Josh? And the direction, the negative 7.5 is only means that it's moving downward, okay? Because we always apply kind of this, you know, plus into the right as a positive. It really doesn't affect the answer so much as that's just the direction that the work is actually going through. Oh, the 3 that we're kind of throwing you off. Yeah. Because then now you can kind of see that. Good. Anybody else have any questions on this and then you just can finish it up? All right. Then I am going to stop the recording.